We'll get started, and I'll spend a couple minutes introducing Bas and the webinar series that we have here. So you can see that this is the Design Society Sustainable Design Special Interest Group, and we have been doing this webinar series for a few months now, and I will just switch over here. All right. So I'm Jeremy Faluti. I'm a professor of sustainable design at TU Delft in the Netherlands, and I'm also specializing in sustainable design. But to introduce to you the Sustainable Design Special Interest Group, it is one of 16 different special interest groups in the Design Society. And the Design Society overall is an interdisciplinary community of academics and industry people as well that get together at conferences and do papers together and have dialogues to develop and promote a robust, usable, and scalable way to design solutions to complex problems. So basically, we're a design and engineering society that is both academic and connected to industry. And we have more than 800 members in 50 different countries. And if you want more information about the Design Society, you can go to the website here, designsociety.org. And today we're going to be having Bas Flipsen talk. He is a colleague of mine from TU Delft. In fact, we share an office, in fact. And he was originally an aeronautical engineer and then became an industrial designer. And he does a lot of quantitative modeling in his design of products. Some of this is engineering, some of it is life cycle assessment for sustainability. And he also has deep experience and expertise in design for repair, which is what he'll talk about today. And some of his experience includes working with iFixit for years. He made a revised version of their scorecard that helps them assess the repairability of how repairable or not repairable various consumer electronics products are. And this ties into his other circular economy research on longer lifetimes and other product circularity improvements. And what he'll talk about today is not quantitative modeling, but qualitative modeling, but it still can greatly improve a product's design, as you'll see. It's all about mapping how disassemblable a product is. And with that, I will switch over my screen and stop sharing my screen, and we will go to Bas. Can you speak up, Bas, or you might
Do
be
you hear me
muted?
now? Do you hear me?
Yeah.
Yeah? All right. All right. Thank you, Jeremy and Daniela, for inviting me to this webinar. I'm pleased to tell you more about our adventures in circular product design. My name is Bas Flipsen. I'm a design teacher at the Delft University of Technology, where I teach mechanics, product architecture design, and circular product design. During my work, I've got loads of opportunities to open up stuff together with my students and learn from them. In the past years, I've been working at iFixit for a long period to research ways of evaluating products on their product architecture and on repairability. And during this period, I worked on repair criteria. I defined certain repair criteria and how to objectively measure them. Based on this research, we have been working on an approach to assess products and improve them on circularity. In this webinar, I'm going to tell you a little bit more about the method of hotspot mapping, which is part of it, where you as a designer can pinpoint circular hotspots in your product architecture. This method can be used to redesign your product, making it circular ready for all recovery strategies as defined by the circular economy scheme. Let's first go back in time. I like these pictures because already back in the 19s, a number of methods were developed to assess the ease of disassembly of products. In those days, these methods were already considered as important for environmental reasons, and in particular for product recycling and remanufacturing processes. Disassembly tables, just like you see over here from Ehud Kroll, we worked on it in 1919 already, and I think we finished. We worked together with Abstables, who's part of one of the participants in this seminar as well. Where we used to quantify the ease of disassembly, and of course we have reversed fishbone diagrams, or on the right side, Ishii and Lee, to visualize the disassembly process. And currently what we're doing is combine those two methods more into a single approach where you can evaluate products on the ease of disassembly, visualize that more, make it more visual for the designer. Recently this work has come under renewed scrutiny because of the Green Deal and the commitment of the EU Commission promoting the circular economy. And France is one of the front runners on this topic and introduced a couple of months ago the repairability index where products have to comply with. And besides that, other recent measures are the material efficiency standards, also known as the EN4555X series, which focuses on the general methods to assess products on all technical loops of the circular economy. And the last pupil to this standard is the EN45554 standard, which promotes a general method for assessment of the ability to repair, reuse, and upgrade energy-related products. So it's all about energy-consuming electronics, like your dishwasher, your washing machine, your refrigerator, but also small kitchen appliances. And this standard was the last standard in the complete series. In the standards, the identification and ranking of so-called priority parts is the first step in assessing a product on repair, reuse, and upgrade. In the standard, a priority part is determined by the likelihood of the part to be replaced or upgraded, the suitability of the part for reuse, and the functionality of the part. This standard touches on the most inner loop of the circular economy scheme, namely repair. On the other hand, we have the EN4555 standard, which promotes recovering materials for recycling purposes and focuses on the recyclability and the recoverability rate and the efficiency of recycling and recovery processes, and thus touches upon the most outer loop of the circular economy scheme. However, both the EN45554 and the EN45555 do not consider the environmental benefits of avoiding the production of equivalent amounts of primary energy and the energy carriers, nor it doesn't include the impacts associated with the energy treatment processes and the cost involved. This is the reason why we developed the Hotspot mapping method, which allows a design to focus on recovery of priority parts, or parts which are going to be which fail the most during use, as well as those parts with a high economic and environmental value, the valuable parts, as we like to call them. Together, those two priority parts and the valuable parts, we call them together the critical parts. And as designers, we want to focus on all these kind of parts, and not only focus on priority parts which fail the most, or exactly built for a repair, and where the EN45554 standard is focusing on, but also we would like to have pinpoint all the parts in the product architecture which are valuable and are valuable at end of life, and also which have a high environmental impact, embodied in high environmental. Together with a visualization, over here you see the disassembly tree developed by Francesco De Fazio, one of our graduate students. He graduated in 2020 or 2019, I'm sorry, at Philips, where he developed this method by disassembling loads of vacuum cleaners. And together with this visualization of the teardown sequence, the so-called disassembly, it's possible to locate these critical parts in the product architecture and assess them on the ease of part disassembly. Hotspot mapping is a method to pinpoint these critical parts, and together with the disassembly map, these critical parts can be located in the product architecture. The Hotspot mapping method is a spreadsheet-based tool, and it's related to Ehud Kroll table. And if you can look at it, and then you see there are some things which are alike, but also there are some new things added to it. The model is a spreadsheet-based tool that indicates ease of disassembly by flagging 5 hotspot indicators. And the first one is time needed to disconnect parts. You have to enter the time for every activity. So you log you disassemble a product. At every activity, you log all the activity steps in this process. You have to measure it by clocking time, and this is the time needed to disconnect the parts. The second one is the difficulty of access. For instance, the amount of force needed to disconnect a part, or the difficulty to approach it. The third one is the parts failure rate or maintenance rate defined by the repair standard as the priority parts, of course. And then we have 2 other KPIs or indicators, the parts economic value and the parts embodied environmental impact. Where the first 2 are activity-based hotspots, the last 3 are parts-based hotspots. And the assessment of the product focuses on product-related aspects and not on context-related aspects, such as the availability of spare parts or health and safety risks. This method consists of 3 steps. First of all, you record the teardown operations in a spreadsheet. That's the spreadsheet we just proposed. And by means of the hotspot identification based on the previous defined indicators. The third step consists of locating the hotspots in the product architecture and figuring out how deep critical parts are nested in the product and what hurdles have to be overcome to reach them. This last step is not discussed in this paper, or at least a little bit in this seminar, but we'll get to it. So what are we doing? First of all, we have to enter different data for every activity which we do. So we dismantle a complete product, we call it a gentle dismantle, and every step, every activity is being logged in the disassembly table. While disassembling the product, the operator logs the necessary data consisting of 5 properties. First of all, the general properties, so the parts or subassembly name, and you see that in the bottom line picture. You see what type of entries have to be entered. There's activity properties, which consist of description of the activities, like removing or ungluing or separating by means of unscrewing, etc. The tools you've been used, like the screws, but also the type of tools being used and the actual time. So you have to clock the time involved in removing the part. Third group is the difficulty of access, consisting of the force involved. And we have 3 levels of force involved, 0 to 5 Newton, 5 to 20 Newton, and above 20 Newton. So high force, where you actually need your complete arms, or you need force where you need 2 hands to disassemble it, or you need low force, which you can do tip of your fingers. This is a very qualitative approach, but in a sense, people can feel at every activity how much force is being actually used to open it up. And also the positioning of the tool is being used. Is it really accessible? Like you can approach it immediately, or do you have to go underneath something? Fourth group consists of functional sensitivity properties and concerns the failure rate, the amount of maintenance and the prioritization of its function. This is often based on priority parts, which is not defined very well. Currently, certain product categories have priority parts, like vacuum cleaners, where one of the wheels on the vacuum cleaner is, for instance, a priority part. It fails the most on average when you have a vacuum cleaner. We have to define these priority parts in this table, and often there are 3 or 4 priority parts which have to be accessible, easy to access while in use. The last group consists of material properties, consisting of the type of material used, like plastics, metals, steel or aluminium, etc., and the parts and its weights. And we're actually going to use that to make a very quick and maybe a little bit dirty, well, a quick and not so dirty LCA of your product's components. So actually you will see which part has the highest embodied impact and also has a very high value. So to illustrate these tools and its functionality, let's run through a case study and figure out the circularity of this Solus A37 blender, which is my own personal one. And it failed because actually the rubber sheet failed during use. There's a lot of lemons coming in there, and the rubber degrade overuse. And then suddenly all the fluids come into the motor, and then the product fails. I noticed that later on they revised it, they revised the design, and for well, a 300 euros blender, I think they were a little bit too. Anyhow, this one I disconnected, I completely disassembled it, I made a gentle dismantle, and you already saw it in the video what we did, and we did it very slow process, and during this period we also logged. The product consists of two major parts, the top half can, which you see on the right, assembly, and the bottom base motor assembly, where all the electronics is confined into a small casing. The teardown is limited to non-destructive operations alone. This means no desoldering or cutting was involved in disconnecting any part from the assembly. And over here you see the bottom half, so the motor. On the left side you see the complete motor unit, which is a large part of this product. And this product consisted of 39 parts, for which 55 disassembly operations were needed. 6 different tools were needed in 12 operations, and all other operations were executed using hands. So that's a good thing, I think. So the less tools we use, the better. The time required for disassembling was critical for more than one part, so I could not pinpoint one single part, which was really difficult to unlock. So especially operation 13, and you will see in the disassembly map, and 14 took a long time to disconnect the bearing module. And this is the small part where the top can had a bearing module where the motor connected with actually the blades in the system. And this bearing module was very critical because actually it filled the rubber sheet, which you see around here, and that's the black around there. Tire, which is around the bearing, it actually broke down and it degraded overuse because of acids, liquids running through it. And by that, it actually also broke down the bearing, and suddenly the motor stopped working. All operations were relatively easy, and only 2 operations showed a yellow flag in the activity column. Operation 12 and 17, 2 priority parts were identified. The rubber sheet, keeping the axis bearing module in place, that's the black thing you see over there, and the axis bearing module itself. Both parts are crucial for functionality and are subject to wear due to high rotational speeds of the axis. And a possible encounter of acid dripping from the jug through the axis bearing onto the rubber sheet, which results in deterioration of the rubber material. 3 other parts are also red flagged due to environmental and economical indicators. That's, for instance, one thing was the glass jug. A lot of glass is being used. The metal blender case, which is completely made out of stainless steel, and the can bottom, of course, which is the part which you see at the bottom. Both the environmental as the economical indicators show these parts which have high embodied environmental and economic value due to the material used and the part's weight. So these parts are very important to, well, get for recycling purposes, and to easily get for recycling purposes. As expected, the glass jug and the metal cases both came out as valuable on economic and environmental aspect because of its build, and this means these parts are worth harvesting in the recycling scheme. In both cases, these parts are easy to reach. This is not the case for the direct current motor, which you see over here. As can be seen from the hotspot table, which I will show you later, the motor has multiple red flags on the 5 indicators which we defined beforehand. This is the hotspot map data sheet where you see the motor over here. Let's see. Works. Yeah, over here you see the motor, and the electromotor is a high weight, 1.6 kilograms, and it took a long time for disconnecting because it was really deep nested into the product. The priority parts, and you see there the high economic environmental impact it has. So this method pinpoints the hotspots, pinpoints different parts which are either time consuming, have a difficult activity, are a priority part, or have an high economic or environmental value. The electromotor should be easy accessible based on this assessment. Because it contains copper and neodymium magnets, it shows up as a priority in both economic and environmental value indicators. Besides these value indicators, it's also scored high on time and priority indicator because of its primary function. Both the value and priority part indicators show the importance of this part, while the time indicator shows the difficulty of accessing this part, and thus shows the hurdles for any reuse or recycling scheme. So there is room for improvement to be found over here. So let's summarize this. The method we propose can be used to systematically evaluate a product architecture and identify hotspots for ease of disassembly. It combines a gentle dismantle of a product, which is always fun to do, and you slowly run through this process of dismantling and learn from it and become more circular practitioner while doing so. It combines a gentle dismantle of a product while logging of all disassembly operations and part properties involved. And then you really get to know your product architecture, and all the components involved. And that really helps in while becoming aware of hurdles and problems and issues you come across. Besides priority part indication, like presented in the EN 4554, it also assesses the product architecture on economic and environmental value of the parts involved. This distinguishes from the standard currently implemented. In this way, it gives designers an improved focus for redesign towards a circular economy instead of only on repair. And that's what we want. Well, based on the case study, concluding from it, we have pinpointed several priority parts. For instance, we anticipated on parts like the DC motor, glass jug, and the metal housing. But we also found some unexpected parts like the rubber sheet and the axis bearing module encapsulated by the sheet. It became apparent that the DC motor is difficult to reach and thus is an opportunity for redesign or improvement, making the blender ready for parts reuse and improved concentration quality during the recycling process. Besides developing these tools as scientific output or applicable output, we try to apply all our learnings and educate people who are interested. Hotspot and disassembly mapping is part of the bachelor course Circular Product Design, as you see over here, where students actually dismantle a product completely and slowly run through the process of disassembling, hotspot mapping, and disassembly mapping, where students gently dismantle products in class and learn how products are put together and the difficulty which come forward when you want to reuse parts or materials. We improve the tools and methods with these students, but also with graduate students working on design for R. In this case, you see a case study from Bente Vermaat, who evaluated different baby car seats, and she dismantled 4 of them, and she also made a disassembly map and a hotspot mapping. We also do that with caravans. It's going to start in a couple of weeks, and with bicycles. And of course, we did that before with Philips. We do that with vacuum cleaners. This is often done in cooperation with companies, like this example, where we try to make more refurbishable baby car seats. The student analyzes the current state using the hotspot mapping, but also disassembly mapping, which is shows over here. sort of like what issue proposes, where you actually show the complete disassembly tree. Based on the hotspot mapping, you can pinpoint where are the critical components or critical parts. In this case, the product architecture can be improved. And in this case, it was a safety critical product for more refurbishable. Over here, we see how Bente came up with a new solution where safety critical parts, which are parts which has to be inspected while coming back before they can be refurbished, be sold again, and how easy it is to get there. So it was in this case more like easy for inspection than easy to. They came up with redesigns, and we developed 3 design strategies to make improvements on the current product architecture. First of all, we have surfacing, where the critical parts are placed more at the surface of the point of entry, diminishing the amount of steps needed to reach a part. Second strategy is to group parts together in a single module, which makes it easy to reach the critical components by taking out the complete module at first, and maybe this component is underneath it or underneath it in the product. We call this clumping. And the third strategy is called trimming, where you, as a designer, should bring back the time needed to disconnect the different parts from each other. And that can be done by changing the interface, by changing time-consuming fasteners. For instance, screws are very time-consuming, but if you need a lot of force, it's also time-consuming. Or besides these kind of students, we try to reach out to the design community, so you all, and have developed on-campus masterclasses and online free and paid MOOCs, massive open online courses. One of them is the circular product design assessment, which you see over here. It's a ProfEd, where we introduce professionals in an applicable way to evaluate current product architecture and let them run through this process of disassembly. In this course, we also educate more on the circularity calculator, where we can see how much money is involved, how much profit you can make when implementing circular strategies. We just finished this first run, and we'll rerun in May 2021. You can sign up for it. Other free courses can be found on the edX platform. For instance, this circular economy MOOC. When you are unfamiliar with product design in the circular economy, I highly recommend you to sign up for this self-paced circular economy massive open online course. It's a mouthful. In general, we think we've developed a simple and applicable approach for assessing consumer products on its ease of disassembly and its circular readiness. This approach is found to be useful for designers by our students to analyze current products on the market and improve their product architecture, making it fit in any of the recovery strategies within circular economy. I would like to show you my last slide, because we actually do this disassembly with students, with professionals, but I like to do that the most with my kids in the backyard. So thank you very much. Hopefully there are any questions. I cannot see you, but you can see me. Thank you.
All right. Thank you very much, Bas. And so we do have a bunch of questions here. I'll just go through these. So first one is a very simple one. Will you share your slides?
Of course, if you like. Yeah, no problem.
Cool.
Am I still visible?
So what's that?
Am I still visible?
You were until you asked whether you were or not, and now I'm seeing some interesting video interference action. I'm not sure what that is. But yeah, so that we can make that available on the Design Society website. And then next question is how to manage trade-offs between disassemblability and safety especially when considering medical products.
Hmm. Yeah, that's a nice one. Started this. Sorry.
Products.
Yeah, what we noticed with, for instance, the car seat, it was a safety critical product. Actually, they're not very refurbishable. Maybe the companies don't even want them to be refurbishable because there are safety critical parts involved. And so during this graduation project from Bente, we noticed that it's actually good to know which parts are safety critical and which parts are less safety critical. How approachable are they in the product architecture? And I think that's same thing accounts for medical products. I think those are safety critical as well. And if you want to reuse parts or reuse the complete product and refurbish it, actually have to look into those safety critical parts. Maybe replace them in a refurbishment scheme before you actually resell it. And that's the same thing. Maybe medical products should be not refurbished, but actually remanufactured, where they are as new when on the market again. Does that answer your question a little bit?
Hopefully it does. I'm reading these questions off from the various readers who have typed them in as text. So next question for you. How to ensure that products with high disassembly efficiency will actually lead to more upgrade, repair, and manufacturing? Like, what's the role of consumer behavior there?
Well, you have to get them back. So if you go into the recircular strategies or circular economy, you really uh, have to have control over the complete cycle. So just selling it and losing it afterwards, losing track of it, is not really circular. You really have to keep track of the product in the circular economy and control those streams. So if you sell a product, it actually has to come back at a certain point towards you where you can either repair it. And there are there are different strategies in the circular economy, which I did not go into because I actually focus more on the product architecture than on the circular economy strategies, where you, for instance, lease out your products. And then actually the product's being used and comes back to you. And then you have control over the complete life cycle of this product. You can maintain it, you can repair it, you can refurbish it, and then bring it back on the market. So different circular economy strategies help out in while making this more circular. What I focus on is merely on the product itself and making it more circularly ready so it fits in those different. So how to ensure products with highly assemblable efficiency will indeed lead to higher upgrade. I think you need to have control over all the complete cycle, not only on the production phase and the selling phase, but also on the use phase and maybe end of life or end of first life phase, end of use.
Okay. And so you're talking about repair by the company who made it, not by the consumers. So not do-it-yourself repair,
Well, there are
but
some discussions on that topic, Jeremy. It's as actually a lot of companies don't like uh, DIY repair, and I can imagine that also because of liability. Uh, but I think there are some things amateur repairers or amateur can actually do. There are simple repairs you can make, you can do, and of course, if you run into the more difficult repairs, and I think about PCB board repair, for instance, that might be a little bit too difficult for DIY repair. And service repair is also an option. I'm open for all, but I think there are some. It's not like yes, repair, DIY repair is the holy grail, or service repair. So I think there's always this twilight zone in between. I don't believe.
all right. And then next question. There are situations in which components or subassemblies are easy to disassemble but hard to reassemble.
Mm,
And should the reassembly be considered too? How would that enhance the tool here?
yeah, yeah, definitely. It's not included yet. And we noticed that, for instance, if you use springs, if you have springs in your product architecture, it's really difficult to reattach them or reassemble them. This happens, for instance, in all the products we disassemble. So the car seats had springs inside, and was was impossible to get them back. Well, the buttons underneath the buttons of vacuum cleaners, there are springs attached as well, and those are really difficult to bring back. Reassembly, I think, is really important. We did not include it in the tool yet. What we noticed on the iFixit website is it always says just rerun the process from bottom to top, and then you reassemble it. But in general, that's not the case. I completely agree on that. It's not implemented like this yet. We are developing this tool, continuously improving it by doing a lot of redesigns and by actually doing it. I think the tool is not so. It's more making you aware of circularity, pinpoint circularity hotspots, and for you as designer to become actually aware of where the flaws are in your product architecture and how you can, as a designer, become creative in what parts should become creative and improve your product. So I think it's not really a scientific approach, but very applicable and makes you aware of where the biggest issues are.
Okay.
So, and
So
then
it's a
after,
guide to help your critical
yeah,
thinking then.
I think it really helps you. If you do this more often, it really helps you in becoming a circular practitioner.
Yeah. All right. Next question. Who's responsible to repair products, and how do you deal with broken cheap products that most people will replace instead of making the effort to repair it?
Yeah. Well, I'm not a fan of cheap products. That's one thing. Everything you buy at the Action will never be repaired. Keep that in mind. So in those $1 shops, it will never be repaired because actually replacement is the goal in that case. So I'm not a fan of cheap products. I'm more fan of more expensive products, which are valuable enough to be repaired. And actually, you have a more emotional attachment to those products often. So it's better to buy a very high-end product than a low-end product. So uh, how you deal with broken cheap products? Well, I hope cheap products are going to be not our future. We're going to deliver, and our students as well. That's why I trigger them continuously. You have to come up with the best solution, not a good solution, which you can pay for, but actually the cheap ass products I don't agree get their diploma if they actually will do that in the professional life.
All right.
So who's responsible to repair a product? Yeah, well, uh, that discussion which I had with companies was that that's all about liability. If, for instance, your kitchen appliance is repaired, and that's something happened in UK, I heard a story about it, that a kitchen appliance was repaired by a DIY amateur repairer, and it actually got flamed while in use after the repair, and this house burned down. So who's liable then? Is that the company? But everybody's looking at the company because it was actually that kitchen appliance failed. But you can imagine that the repairer is, in this case, liable. Papers say something different. So keep that in mind. That's why I'm not completely 100% convinced that everything should be repaired by do-it-yourselfers. But actually, I think service repair is not that strange option. And keeping the money flow as well. So who's
Mhm.
responsible for repair of a product? Well, in a sense, is the guy or girl who's repairing it.
All right. And what's your experience using the tool in a workshop setting? This person asks, we plan to use the tool for a workshop with 10 people, applying on a power tool such as a heavy duty drill.
Yeah.
How much time would you recommend to plan for a rough hotspot mapping?
Or I think disassembly costs you about 1.5 hours. We do this in workshop environments, so we have our students work on it. They disassemble products. We always tell them to bring products of their own, which are not too difficult. This hotspot mapping made with 50 components. Do that in an hour, 1.5 hour. It's doable. We do this in the Profit course as well. People do that at home. And sometimes they have a real large product with more than 200 components. We did that with a bicycle, for instance, which had more than 300 components, and that takes a while. So it's if you have simple products with 10 to 20, maybe 50 max components, you can do it in 1.5 hour. First do the disassembly map. First do the disassembly. I always propose to do that, videotape that one, and based on the video, you can actually fill in the hotspot mapping and also do the disassembly mapping. Yep.
All right. And I'm curious, I don't know if you have any extra slides, but the my favorite part of your work is the visual hotspot maps, the
Yep.
tree diagrams. Um, do you have any extra slides where you could show like the difference between a vacuum cleaner that is badly designed for repair versus well designed for repair?
Um,
Or if you don't have that up,
oh,
that's
I've
fine.
got this one. This is a disassembly map of a vacuum cleaner, where it actually shows these are the parallel disassemblies you can make, and not here, but critical components are really way down. It takes you a long route to get there. So actually, these are all activities involved. So there's a high force involved over here. This is the PH00 screwdriver being used. Then we get to part 8, for instance. Do you see my?
Can't see your cursor.
We can't see your cursor. Oh, let's see. Yeah. Now, do you see my cursor? Do you?
Oh, I see a little pink dot that then disappeared.
So first of all, this is the. Oh, it freezes up.
That's okay. I don't want your system to crash again.
It's freezing. Sorry, crashes. My PowerPoint crashing now.
All right. Never mind. So we'll leave that. But then I've got one more question for you here, or it could be a couple more. But uh, how might this help score the repairability of a product? Like, can it help to quantify product X is more repairable than product Y?
Should, but currently it's not. I've been working with iFixit on repairability scoring and especially on objective scoring, and actually you can actually compare different products. We have developed what we think is a very objective tool based on 9 criteria, which are context-based criteria, but also having a manual available, for instance, spare parts for a certain period availability is one of those context-related criteria, but also the ease of disassembly. And what we noticed there, and we're still working on it, is time. So how to measure time, or how to clock time, or how to actually simulate time. Everybody's looking into the most work measurement system, which is used for assembly lines. So to actually design assembly lines, and every activity has a certain amount of time. It takes a certain amount of time into account, and then when you count them up, you know the total time to get there. I think most really works, but there are some new difficulties in products now, which were not there, or to a lesser extent, in the 1990s. Different ways of interfacing and different types of fasteners like glue. And what we noticed while disassembling a lot of smartphones at iFixit is that degluing, or actually pulling stuff from the back cover, is really difficult to measure and really difficult to come up with a proxy time, as we call it. At currently, we're working on that and how we can define the proxy time for degluing for instance, batteries which are glued in, or the complete casing which is glued on top of each other. That's a really difficult one. Next to that, there's this row of snap fits, for instance, which is also difficult. Sometimes it's a really easy snap fit connection. Sometimes it's really difficult to disconnect them, or even breaks. So those are the different activities which are not currently not really um, well caught in an objective manner measure in this case. And I think if you look at EN4554, it shows that you can use the EDIM method, which is a method developed by the KU Leuven, which is based on most work measurement systems. And actually, the standard only focuses on the number of steps taken before it reaches a critical component, or priority part in this case. And what we know there's a bad relation between the number of steps before reaching a priority part and the time it will take to reach that one. It's not a one-on-one. It's not linear correlation. It differs much, and that all has to do with glue, snap fit use, different type of fasteners being used, and we're trying to catch that. We're trying to get this into a system, but currently we don't have it. So we don't have proxy times. And if we have that, I think we actually do a much, much better job. We simulate the ease of disassembly instead of measuring the ease of disassembly, because now it's operator dependent. I can do it very easily because I'm used to doing opening up stuff, but I can imagine if you never opened up a product, it actually takes a long time before opening it up. So to make it more objective, we normally ask our students to disassemble it, reassemble it again, and then do the disassembly again in a normal way. And actually, then you know what to do, you know what the next steps are, then you don't come into the hurdles, and then time is a better measure than when you do it.
Interesting. So to score things, you basically want to score it how not necessarily an expert would, but the way that someone who knows what they're doing would.
Yeah, yeah.
Interesting. Okay. Well, those were all the questions that we had, and we're getting close to the end here anyway.
Yeah.
So I will just go back to sharing my screen here.
There was a question about
And
did you check if the tool is repeatable?
oh, ah,
That's one of those questions I can understand why you're asking this. Then again, I think it's a tool which really helps you out to become a circular practitioner instead of being a scientific repeatable. We really tried that one, and that was the discussion answer I gave before this one. We really tried to make it more repeatable, so very objective, but we noticed that it's quite and time is one of those issues. It's not really defined very well. Time is defined, but not in this this tool. Yeah.
yeah,
So maybe
great.
I have to
Yeah.
answer that question with no. I'm sorry.
Yeah, well, it just shows further research is required.
Yeah, I always say it's an alpha version now, and we improve it every day. Yeah.
Yeah. Well, great. Thanks very much, Bas. So that was hotspot mapping for product disassembly. And for those of you who are interested in the rest of the webinar series that we have here, the next one that's coming up in November will be our first industry person rather than an academia person. And that'll be Adam Björk from Volvo, and they're talking about their construction equipment and how that works in the building industry. And then the one for December will be Anna Patis from Grundfos on their product development solutions as well. And so thank you very much for everyone who has joined us for this webinar, and we'll have the recording posted online on the Sustainable Design Special Interest Group website. And thank you very much, and I hope you all have a good day.